Hello everyone, welcome to Unit 4. So this unit we're going to be looking at a little bit more in depth into exponential functions. If you recall way back at the beginning of the course, back in Unit 1, we looked at how to convert um, recursive functions into explicit functions. And one of the explicit functions that we looked at pretty well in depth was the exponential function, how a geometric recursive function turned into something that is exponential. We are going to bring that back a little bit for the first couple lessons here and kind of review a little bit of the connection between there. Not so much a review of the uh, recursive function itself, but more on the property that lends to exponential functions. And then over the next few lessons, we'll look at more in depth on how those exponential functions operate. Okay, um, so let's jump right into it, shall we? All right. So our first video is going to be on lessons 1 and 2. So we're kind of doing this combined. Again, this is more of a review of concept, if you will. And so we're going to do this just through some problems and situations that can come up. So here we're looking at the ideas of growth and decay, and you might remember those topics again from Unit 1 and how we can represent something that is growing exponentially and then something that is decaying. Um, the main difference between the two, if you recall, was in what we had a growth factor, right? And if you recall, we had an exponential function that looked a little bit something like this. We had, like, say, you know, uh, I don't know, y, I could say y equals, but we even had like a of n equals. So like a of n equals, um, and we had maybe, 5 times, let's say 1.25, to the n power. And sometimes we use n minus 1, depending on whether we started at 0, we started at 1. So we're going to have a chat about that again as well. So that will come back. But if you recall, this here was called the growth factor. And the growth factor determined whether or not the function was increasing or whether it was decreasing. And in this particular case, the function is increasing. It's increasing by a rate of 0.25, so it's a rate of 25% increase. Uh, if we had a situation where, and the more common situation that we saw was this one. If we erase this here and we had instead um, 0.75. Now that was a more common situation. It meant that 75% was retained at each step, and that's considered decay. So here we're going to bring that back again and take a look at the connections that we made back then and how they're going to relate going forward. Okay, so for starts, let's look at just a few samples of questions that can come up. So here's a good example, a passport photo. So a passport photo is a small photo in a little booklet. Many of you probably have a passport if you've been out of the country or are planning to. But generally, the photos that are taken um, are obviously going to be much smaller than your face, so they have to be shrunk. So here's a person, Elena. The distance from the top of her head to her chin, the entire height of her head, is 150 millimeters in an image. For a US passport photo, this measurement needs to be between 25 and 35 millimeters. There's a very specific standardized size for the book, right? Okay, so let's say we have an image and it's been scaled by 80%. Okay, so what does that mean? Scaled by 80% means that it's going to have 80% of the scale every time we apply it. So this is the same as, when we say 80%, we're going to multiply by 0.80 because we're finding 80% of the height. So another way to look at it is 80% of the height. That's where we're going to mean by scaling. And so you're going to hear scaling a lot in this unit. Okay, so from here, we're going to scale it 3 times, right? So what does that mean? We're going to scale by 80%, but then we're going to scale the new one by 80% as well. And then we're going to scale the new one by 80%. So it doesn't mean that we're going to scale by 240% because we can't do that. So instead, we're going to shrink by 80% and then take the new one and multiply by 0.80 and then multiply by 0.80 and then multiply by 0.80. So what happens when we repeat this multiplication many times? We end up with exponents. And so there's that connection that we used back in Unit 1. So we're going to take 150 millimeters, right? And we are going to multiply it times 0.80, but we're going to do that 3 times. Instead of multiplying it 3 times, we're going to use an exponent. So it'll be 0.80 to the third power, and then I just have to go ahead and calculate that. So as far as calculations goes, I'm just going to pull out a calculator here. Normally, I would just use the calculator on screen. I'm just going to do this quickly here. 150 times 0.8 third power, 76.8. Okay, 76.8 millimeters. Okay, so for the remainder of this, I'm going to go ahead and find my um, on-screen calculator. There it is. Perfect. Okay, and we'll do the next one 6 times, right? So let's say we did it 6 times. So 150 times 0.8 exponent 6, 39.37 meters. Still too big because it has to be between 25 and 35 centimeters. So how many times would we need to scale this, right? Well, clearly it looks like 39 is just a bit too high. Maybe if we do this 7 times. So what I can do is I can hit the up arrow, press enter, bring back the last calculation. Let's change this to 7. Yeah, definitely at least 7 times. Because that'll drop it to 31 centimeters. And then less than 25. Well, let's keep doing this. And let's see what happens. If I do 8, 25.16. Ooh, so close, but that's still above 25. 20. So we're going to do 9 times. Okay. And so from that, what that means is that if the measurement has to be between 25 and 35 millimeters, ultimately we can provide the scaling 7 or 8 times. Uh, you need 7 to get it small enough, and then at 9 times it's too small. So 7 or 8 is going to work. Okay, so this is the kind of math that we're going to be bringing back this unit. Okay, so let's look at some more in-depth exponential work, okay? On May 12th, a fast-growing species of algae is accidentally introduced into a pond in an urban park. Uh-oh, this sounds bad. Area of the pond doubles each day that the algae covers. If not controlled, the algae will cover the entire surface of the pond, depriving fish in the pond of oxygen. Okay, that is bad. At the rate that it is growing, this will happen on May 24th. Okay, that's 12 days. Algae grows fast. Is it algae? Algae? I guess it depends. I've always said algae, but I guess it could go either way. Anyway, that's irrelevant. On which day is the pond halfway covered? Okay. All right, that's an easy one, right? So what, 12, 24. So what, May 18th? No. Careful. The area of the pond that the algae covers doubles each day. If not controlled, so this will happen on May 24th. So on May 24th, the pond is fully covered. Then we can assume that it doubles each day. Well, if it doubles each day, what did it double from to fill the pond? It must have doubled from halfway, right? So believe it or not, on what day is the pond half covered? May 23rd. And the reason why is because when you double half, equals the whole pond is covered. So kind of interesting to think about. Doubles each day. I'll probably catch a few of you on this one. Okay, so now on May 18th, Claire visits the park. Um, park caretaker mentioned to her that the pond will be completely covered in less than a week, which is true. The pond caretaker is correct based on the definition that we already know because it's a 6-day difference. But Claire thinks that the caretaker must be mistaken. So, why would we find this hard to believe? Think about it. On May 18th, what do you think the pond looks like? Now, we already know it's not half, right? Because 18, yes, is half the days. But remember, it doubles each day. So let's think about it this way. If it doubles each day, then on May 23rd, right? We already know that on 5/23, half the pond was covered. But then what must have been the status on 5/22? Well, if half the pond is covered on the 23rd, then what gets doubled to make a half? 1/4. So another way to think about it is if going forward, each day the pond doubles. If we were to go backward in time, then the algae gets cut in half at each previous day, right? And so we can keep going back. And what you're going to find is not much of the pond is covered. 5/19, it's 1/32. And then on 5/18, it's 1/64. So on May 18th, only 1/64th of the pond is actually covered, which is a small fraction. That is less than 2% of the pond is covered. So it does not look like there's much algae in it at all. So you can understand that Claire is probably going to look at that and say, oh, that's not bad. But if it doubles every day, that's all it takes. So let's continue the pattern then. What fraction of the area of the pond was covered by the algae initially? Well, there's a couple ways you can do this. One, you can keep following this pattern. But another way to think about this is with exponents. Because look at the denominators. 2, 4, 8, 16. So this is 2 to the first. This is 2 squared. 2 to the third. 2 to the fourth. 2 to the fifth. 2 to the sixth. And the pattern were to continue. And so we could go 7 days, 8 days, 9 days, 10 days, 11 days, 12 days. And so it becomes 12 days back, which is a pretty big number here. And you could even think of it as 1/2 to the 12th power as well, because that's essentially the same thing. You're halving each time you go back a day. So it becomes point 5 exponent 12. Oh, scientific notation. So sometimes when the numbers are very small, it might give you the answer in scientific notation. Um, by the way, this is actually as a fraction. Well, let's see, what's 2 to the 12th? 4,096. So this is equal to 1 over 4,096. As a decimal, if you would have moved this 4 spots over. So what's going to happen is it's going to equal 0.0002 or 0.02%, all of which are all equal. So that is a very small fraction of the area. Just a tiny little bit of the pond has some algae in it. But if it doubles every day, all of a sudden, kaboom. So this is again the nature of how exponents work, and especially something like doubling. Doubling makes things grow really, really, really fast. Okay, so now let's look at some other problems. Not everything involves doubles and halves, so let's see what else we can do. Okay, ooh, money. Priya borrows $160 from her grandmother. Hmm. Each month she pays off 1/4 of the remaining balance that she owes. Okay, responsible grandkid. I can understand that. I mean, if my daughter did this to me, I would be totally okay with it. So, what amount will Priya pay her grandmother in the third month? Okay, so here's the thing. We're going to look at a balance. So, she's going to pay off 1/4 of it. But then the remaining balance, she's then going to pay 1/4 of that. And then the remaining balance, 1/4 of that. So, I think here we should make a table. So, month number 1, she owes $160. So what's 1/4 of 160? Well, that's $40. So she's going to pay $40, and that's equal to $120. Month 2, she owes $120, and she's going to pay off 1/4 of that. Well, what's 1/4 of 120? It's $30. And now she owes 90. For the third month, she owes $90. Now she's going to pay 1/4 of that. And 1/4 of that is 45. And then half of that is 22.50. So she's going to pay 22.50. Now, I guess suppose she would just pay regular dollars at this point. Um, but we're going to go by exactly as it says. If she pays 1/4, she pays 1/4. And so how much is going to be left? 67.50 it looks like. Okay. So again, because the amount that she owes gets less and less, the amount that she pays becomes less and less. Now, one thing that we looked at in terms of asymptotes back in Unit 3, when we dealt with polynomials, was if we were to keep doing this process forever, will she ever actually pay off how much she owes? And the answer is no. She'll always owe at least something because she's only going to pay off 1/4 of the balance. So there's always going to be some balance, even if it's just a small amount. There's going to be some balance left over. Okay, so now what about this expression? 160 times 3/4 to the third power. So where is that coming from? Well, let's consider this. If you pay off 1/4 each month, well, how much is left? So 3/4 is left. Right, so you're paying off 3/4 each month. Right? So your balance is being multiplied by 3/4. So for the first month, you can do, if you were to think about it, you could do like P, your amount that you owe, minus, you're paying 1/4 of P, but 1 minus 1/4 is 3/4. So 3/4 P is left. So if you start off with P, amount that you're paying, that you've borrowed, and you lose 1/4 of it, you've paid back 1/4 of it, you still have 3/4 of it left over. But now let's look at the next month. Now that goes on the next line, right? So 3/4 P. But then what's going to happen? 1/4 of this is going to go away, leaving you with, so with the balance that's going to be remaining is 3/4 of that. And you're going to be left with 3/4 of 3/4 of P. And if we were to repeat the process, you're going to have 3/4 of 3/4 of 3/4 of P, which is where this comes from. So I'll highlight this. And so each month, 3/4 of the balance is remaining. 1/4 of it is being paid. So that's where exponential functions come into play. And every time we calculate a function or we work with a function, notice that they're always written in terms of the leftover amount, not what gets paid or not what gets lost or not what's gained, but like the total that's remaining after some changes happened, whether we pay a bill or whether bacteria grows. It's not how much it grows by, but the total. So we always think about from that perspective. Okay, next question. The tuition at a college was $30,000 in 2012, 31,200 in 2013, 32,448 in 2014. Tuition has been increasing by the same percentage since the year 2000. Yay! Lucky you guys, right? Okay, so the equation C of t equals 30,000 times 1.04 to the t power represents the cost of tuition um, as a function of the number of years since 2012. Okay, so what do these numbers represent? So remember we talked about this, again during Unit 1, right? How the 30,000 is like a base cost, a starting value. Oops, not based. I'm making a turkey here. Oh boy, I guess it's late. Okay, uh, base cost. So it's some starting value that we have, right? And then what does the 1.04 represent? It represents the fact, it's like a growth factor. We talked about the growth factors at the beginning. So 1.04 represents the fact that it's growing each year. And so the question then is, how much is it growing by? Well, look at the difference. So it's growing from 30,000 to 31,200. So it's a growth of $1,200, right? So it's a growth of 1,200 out of the 30,000. So what's 1200 divided by 30,000? 0.04, which represents a 4% increase. Now, how can we tell that from the original number? Well, the original number is 1.04. So what does the 1 represent then? If I got 1.004 here, but in the function there's this 1, what does the 1 represent? The 1 represents the original 30,000. The 1 is what makes it grow. When you multiply by a number greater than 1, it makes the function grow in value. And if you multiply by a number less than 1, it decreases in value. 1 is kind of like, remember, you multiply by 1, the value doesn't change at all. So it's kind of like the borderline, if you will. So the 1 represents the fact that I could add the 30,000 into this. It represents one whole 30,000 amount. And so I could do 31,200 over 30,000, and that gives me 1.04. So the 1 represents the original 30,000. And it's the whole amount plus the growth instead of just the growth itself. So when we look at the growth factor, okay, if I see an exponent, if I see a base of 1.04, I know that the 1 represents the original amount, and this 4 then, therefore, is the increase. And that's important. So if it was 1.07, it's a 7% increase, so on and so forth. Okay, so what about C of 3? So let's go through, right? And we can find what's going on. So 3, what does 3 mean in this situation? Well, 3 is replacing t. What does t represent? T is the number of years since 2012. So if it's 3 years past 2012, that must be 2015's cost. Let's go ahead and find it. So 2000, well, we can't use 2015, right? So we have to use 30,000 times 1.04, and then we're going to do exponent, and we're going to do 3. 33,745.92. There you go. Did I do the math right? I did. Okay. All right. So write an expression to represent the cost of tuition in 2007. Now, wait a second. Can we do that? Because doesn't this function start at 2012? Oh, but it does say the tuition has been increasing by the same percentage since the year 2000. So if that's the year 2000, like, what can we do? How can we rewrite this? Because if it's been the same year since 2000, yet the value that we have is for 2012. So could we rewrite this function? We could shift it back to 2000. Or we could realize that 2007 is 5 years prior. And if it's 5 years ago, does that mean we could use a negative? So could I do 30,000 times 1.04. Now, to the negative 5, because that was 5 years before 2012? Well, I could, because this function was written from a base of 2012, so to find 2007, we could use minus 5. Now, here's a question. Why does that work? So let's say we did it the way that we did this back in Unit 1. If we did this back in Unit 1, what we would do is we would realize that we're given not the first term, but we're given the 12th term. And so because we're given the 12th term, we could say that it's, t minus 12 because we're given the 12th term instead. So if we're given the 12th term, now all of a sudden t represents years from 2000. And then now we can plug in, 7 years from 2000, 7 minus 12 is equal to negative 5. So we still get the same negative 5. So what that must mean is that it doesn't really matter what number you consider as your starting value. You can always convert it back to the correct year. So if you need to go backwards from the current year, assuming you know that the function works and we're told that it does, then I can use a negative exponent to represent going back to some time in the past. That's super important. We were never able to do that before. So we didn't do that in Unit 1, but now we realize that we can because negative exponents have a property. We've discussed them and we've kind of developed how they work. We did that last unit. So now we're good to go. And so now we can actually calculate this. So let's go ahead and do it. 30,000 times 1.04, and we can do an exponent of negative, not point, negative 5, wrong negative sign, and we get 24,657. Which is smaller than the current tuition. Because, as you can imagine, we're undoing, several years worth of growth. We're undoing 5 years of 4% growth. So if you go backwards, the 4% increase becomes a 4% decrease. Fascinating. Actually, tell you the truth, that's not really a 4% decrease, but that's a conversation for another time. So this makes sense, though, that earlier tuitions are going to be cheaper. All right. So you see what we're kind of doing here? Okay. A few more things we can do. A small business bought a van for $40,000 in 2008. Van depreciates by 15% every year after its purchase. So classic car problem. Yeah, this happens. Cars lose their value. Especially business vans, right? And business vehicles because they get used a lot. So which graph is going to correspond to the value of this van? Okay, so 0, we've got 2008, right? And then on the x-axis, we're going to have years since purchase. So which of these graphs makes sense? Okay, now obviously, starts with 40,000, right? So which graph is immediately out? That one. Doesn't even start at 30. It starts at 30, not 40. Okay, the rest of the graphs start at 40. Okay, so let's think about this. Okay, which other graph? Okay, the van depreciates by 15%. Okay, so what does that mean? Depreciates means loses value. Which graph is out? Not this one. That goes up. Okay, so now we end up two graphs that kind of go down a little bit over time. Okay, so 15%. So let's look at the difference between this one's kind of like goes down kind of carefully. This one swoops way down. So it goes from 40,000 to 20,000 to 10,000. Does that sound right? Hmm. This is losing half value. That doesn't seem right. Ah, must be this one. So, but here's one way that you can check it out. You can actually do with the division, do 34,000 divided by, because that's the first year's value, divided by the original of 40,000. And you will get 85. Now, hey, where does the 85 come from? Well, 15%, the remainder must be 85, right? If you take away 15% of its value, what's left is 85%. So each year, so when a van depreciates by 15%, what this means is it retains 85% of value. So remember, and this is going to be important for things that decrease, for what we call exponential decay problems. Exponential decay functions are written from the perspective of how much is left, not how much is lost. So the 15% is not in the expression, the 85% is. All right, so now that we know that, let's use that and write an equation, right? So the equation for this, right? So V of t, van of t is going to equal, so we start with 40,000. My starting value is 40,000. My growth factor is 0.85, and it's going to be t. So all we have to do is plug in t for 8, or 8 for t, whatever, 40,000 times 0.85, exponent 8, it's worth $10,900. $10,900. Okay, now in that same year, 2008 now, the business bought a second van that cost $10,000 less than the first van and depreciates at 10% per year. Okay, so they bought the van in 2008. So they actually bought two vans at the same time. So this isn't 8 years later. They bought the vans at the same time. So they bought a second van that costs $10,000 less, depreciates at 10,000 per year, 10%. So what is the function for that going to look like? So again, we have the original function. So let's call it v sub 2, second van, t, is going to be 30,000, $10,000 less. Now, if it depreciates at 10%, how much is left over? 90%. Okay. And so, again, look at the connection here. I'll write it again just to make it perfectly clear here that, 10% gone equals 90% left. And so the value here that we're going to use is 30,000 times 0.90 exponent 8. So it's less value. So it's a cheaper vehicle, but it retains its value. 12,914. Interesting. So cheaper vehicle, but retains its value because it doesn't depreciate as fast. So depreciation, having a smaller depreciation having it retain its value seems fairly important. On the same coordinate plane as the graph you chose in the first question, sketch a graph that shows the value of the second fan as a function of years since its purchase. Okay, I guess that means we're going to have to go back here and we can look at this graph. You know what? Why do that? Let's look at the graph on Desmos, shall we? So let me go ahead and pull up Desmos. And I believe you can see it. I believe you can see it. Uh, should be able to. Let's pop the two equations in here. Let's do 40,000 0.85 to the t. Actually, we do x. It likes it when I do x. So let's cap lock. Do y equals. And then the next line, y equals 30,000.9 to the x power. All right. Here's the two graphs. Okay, interesting. Wow. Okay, so you can kind of see what happens here. So they come close. Now, I know the graphs are kind of a little, but if we go way up here, looks like they're going to cross it somewhere. They're getting closer and closer to one another. Maybe I should try to extend out this axis a little bit. So let's do x-axis. Let's do x-axis maybe from 0 to 10. And let's do the y-axis from 0 to 50,000. Okay, so here's the two equations for you right there. Okay, hey, and it looks like they have a nice little crossing spot right there, right? So in this particular case, the first value, so the first fan they had a higher purchase value, but pretty quickly it depreciates to lower than the second fan because the second fan retains its value better over time. And it looks like just past 5 years. At a point just past 5 years, uh, the first fan's value drops below that of the second fan. And will always remain that way. They will continue forever to be worth, um, the second fan being worth more after 5 years. Okay, so that's probably going to answer a few questions here. Oopsie, kind of messed that up there. There we go. All right. So there are lots of ways to represent an exponential function. We could write it with functions, graphs, tables, charts. Um, in this particular case, you have a city that increases by 10% each year, so the growth factor is 1.1. And so, really, our first main takeaway from this is the idea of growth factor and growth decay. Um, so, some of this was familiar from previous units. Some of it may be a little bit new, especially with the negative exponent, can now be used. Um, so, there's lots that we can now do with this. So, the next things we may discuss, what about fractions? Could we do fractions with exponent? What would that represent? Maybe half a year? Sure. Why not? What if we had the reverse problem? What if we wanted to know at what point the population hits 25,000? What month? In somewhere between 92 and 93. What if we want to know at what point the population hits 30,000 or 100,000? Could we figure that out? Sure. All that's coming up. All right, guys. That's it for the year. It's lessons 1 and 2. Take care. Have a good night.